in part B, we're going to solve equations 1 to 3 for the three possible cases for lambda. 1 lambda is less than 0, 2 lambda is equal to 0, and 3 lambda is greater than 0. I've also labeled the two ordinary differential equations we just derived, equation 6 and equation 7. Okay, so the first case we want to analyze is lambda is less than 0. Okay, if lambda is less than 0, that means that we can write lambda as minus omega squared, where omega is just some real number. Okay. Now, if we substitute this expression for lambda back into equation 6, what do we get? Well, equation 6 then becomes d2x, dx squared minus omega squared x is equal to 0. And you should know from your lectures that this equation, the second order differential equation, has solution x equals a cosh omega x plus b sinh omega x. Okay, and a and b here are just arbitrary constants to be determined. Now, to determine a and b, we need boundary conditions. Okay, so if we return to our initial boundary value problem at the start of the problem, boundary condition 2, that told us that u is equal to 0 on x is equal to 0. Now remember that u is equal to x times t, so boundary condition 2 is the same thing as x of 0 times t of t is equal to 0. Okay? Which means that either x of 0 is equal to 0 or t of t is equal to 0 for all t. Now, if t of t is equal to 0 for all t, that would mean that u is equal to 0, and we would recover the trivial solution. In this problem, we're not interested in trivial solutions, so we're just going to neglect the second solution here and instead focus on the first one, x of 0 is equal to 0. That's the boundary condition we're going to use. Okay, now I'm just going to label the second order differential equation here. I'm going to label this equation 8, and the first boundary condition we want to impose on 8 is 9. Okay, now if you follow the same procedure but with boundary condition 3, you'll find that x of L is equal to 0. Okay, and I'm going to call that equation 10. Okay, so to determine a and b in our solution for x, we need to impose boundary condition 9 and boundary condition 10. So let's do that now. Okay, so if we impose boundary condition 9 in our solution for x, we're going to get a cosh of 0 plus b sinh of 0 is equal to 0. Okay, now recall from your lectures that cosh of 0 is 1 and sinh of 0 is 0. So this equation here, that's the same thing as saying that a times 1 plus b times 0 is 0, which of course would tell us that a is equal to 0. Okay? So to determine b in our solution for x, we need to impose boundary condition 10. Okay? So if we impose boundary condition 10, what do we get? Well, we're going to get a cosh of omega L plus b sinh of omega L. And that has to be equal to 0. But recall that A is 0, which tells us that B sinh of omega L is equal to 0. Now sinh of omega L here is not equal to 0, so we can divide both sides of this equation by sinh of omega L, which will tell us that B is equal to 0. Okay, so that tells us that A and B are equal to 0, which means that x of x is equal to 0. And if x of x is equal to 0, that tells us that u of xt is equal to 0. So in conclusion, for lambda is less than 0, we have no trivial solutions. Okay, so let's move on to the next case we have to analyze, namely lambda is equal to 0. Now if lambda is equal to 0, then equation 6 would become, equation 6 will become d2x dx squared is equal to 0, which of course can be integrated twice to obtain x of x is equal to ax plus b. And similarly, to determine a and b, we need to impose our boundary conditions, namely boundary condition 9 and boundary condition 10. Okay, so if we impose boundary condition 9, that's x of 0 is equal to 0, that would tell us that a times 0 plus b is equal to 0, which of course just tells us that b is equal to 0. Okay? And to determine b, we need to impose boundary condition 10, namely x of L is equal to 0. So if we impose boundary condition 10 in our equation for x, that would give us that a L plus b is equal to 0. And of course, remember that b is equal to 0. This just tells us that a L is equal to 0. And of course, L is not equal to 0, so we can divide both sides of this equation by L to get that A is equal to 0. So as in the previous case, we have x is equal to 0, and hence u is equal to 0. So as for lambda is less than 0, there are no non-trivial solutions for lambda is equal to 0. Now the final case we have to analyze is lambda is greater than 0. Now for lambda is greater than 0, we can write lambda as omega squared, where omega is just some real number, because any positive number can be written as some real number squared. Okay, so in this case, if we substitute our expression for lambda in terms of omega into equation 6, what do we get? Well, equation 6 then would read d2x dx squared plus omega squared x is equal to 0. Which of course is just the regular simple harmonic motion equation. So we know that this differential equation here is going to have solutions a cosine of omega x plus b sine of omega x, whereas before a and b are arbitrary constants. And as in the previous cases, to determine A and B, we need to use our boundary conditions 9 and 10. So if we impose boundary condition 9 in our solution for x, that would give us a cosine of 0 plus b sine of 0 is equal to 0. Of course, cosine of 0 is 1 and sine of 0 is 0. So this is the same thing as saying that a is equal to 0. Okay. To determine b, we need to use boundary condition 10. So if we impose boundary condition 10 in our solution for x, we get a cosine of omega L plus b sine of omega L. And that has to be equal to 0. But we know that a is equal to 0. So this first term here is just 0. And we're left with b sine of omega L is 0. So we're left with b sine of omega L is equal to 0. Which tells us that either sine of omega L is equal to 0 or b is equal to 0. Now if b is equal to 0, we would have both a and b equal to 0, which would imply that x is equal to 0 and hence u is equal to 0. So because we're interested in non-trivial solutions, we're going to neglect the second solution here and just focus on the first, namely sine of omega L is equal to 0. Now, if you picture a graph of sine of x, you'll see that at every multiple of pi, sine is equal to 0. So if sine of omega L is equal to 0, that would mean that omega L would have to take the values pi, 2 pi, 3 pi, and so on and so forth. Here we're only interested in positive multiples of pi because both omega and L have to be positive. Okay? Well, another way of writing this would just be omega L is equal to n pi, where n here is just a positive natural number, namely 1, 2, 3, and so on and so forth. Okay, now recall what was omega. Omega, we wrote that lambda is equal to omega squared. So that would mean that omega is equal to the square root of lambda. So if we replace omega by the square root of lambda, that would give us that lambda L is equal to n pi, which can be easily solved for lambda to get that lambda is equal to n squared pi squared over L squared. Okay? Now to summarize what we've concluded here, we've shown that our equations only have non-trivial solutions when lambda takes these special values n squared pi squared over L squared, where n is just 1, 2, 3, so on and so forth. So these lambdas are the so-called eigenvalues of the problem. So this problem only has non-trivial solutions when lambda takes these special values n squared pi squared over n squared. So to emphasize that lambda depends on n, I'm just going to write lambda as lambda n from now on. Okay? Now for each lambda n, we have a corresponding solution to our x equation, namely xn. So if we substitute our lambda n values back into our equation for x, we get that the corresponding xn's are given by a sine of n pi x over L. sorry, this is meant to be b, my mistake, b. And again, to emphasize that these solutions vary with n, I'm going to replace n with bn. Okay, so for each value of n, we have a corresponding solution xn, which is given by bn sine of n pi x over L. Okay, but remember here, what was our original goal? Our original goal was to solve for u, not x. And recall that u is equal to x times t. So to determine u, we also need to determine what t is. Now, how are we going to determine what t is? Well, if you recall equation 7 all the way back here, we have an equation for t. So let's just solve that equation for t. And remember that lambda here is given by lambda n is equal to n squared pi squared over L squared. So if we replace lambda in equation 7 with lambda n, equation 7 then becomes d2t dt squared plus lambda n c squared t is equal to 0. And to emphasize that these t's depend on n, I'm going to write the t's as tn. Okay, well, this is just a regular simple harmonic motion equation with omega squared equal to lambda n c squared. So we can easily write down the solution to this equation. The solution is Tn of t is equal to Cn cosine of the square root of lambda n ct plus dn sine times the square root of lambda n ct. Okay, and recall that lambda n is given by this equation here. So if we replace lambda n in our solution for Tn with these values here, we can write our solution Tn as Cn cosine of n pi ct for L plus dn sine of n pi ct over L. Okay, and I'm going to just write my xn's as equation 10 and my tn's as equation 11 for future reference. Now, to determine the corresponding solutions for u, we just need to multiply x and t. Okay, so let's do that. So the corresponding solutions for u, I'm going to write them as un of xt. And that un has to be equal to xn of x times tn of t. Now if we replace xn and tn with equations 10 and 11, what will we get? Well, tn would be cn cosine of n pi ct over L plus dn sine of n pi ct L, and that would be multiplied by xn. And xn, we know from equation 10, is bn bn sine of n pi x over L. Okay, so we can bring this bn into the first term here, and then we would have bn cn and bn dn here. So we can just redefine that constant, those constants, and write our solution un as alpha n cosine of n pi ct L plus beta n sine of n pi ct for L, all multiplied by sine of n pi x for L. And here, alpha n is just Cn times Bn, and similarly, beta n is just Dn times